Welcome back. In the last video, we discussed some different loss function options for our classification models. So we learned that if we're working with binary cross entropy or binary classification problems, we want to use binary cross entropy. And PyTorch has two different types of binary cross entropy, except one is a bit more numerically stable. That's the BCE with Logits loss because it has a sigmoid activation function built in. So that's straight from the PyTorch documentation. And that for optimizer-wise, we have a few different choices as well. So if we check out this section here of the PyTorch book, we have a few different loss functions and optimizers for different problems and the PyTorch code that we can implement. But the premise is still the same across the board of different problems. The loss function measures how wrong our model is. And the goal of the optimizer is to optimize the model parameters in such a way that the loss function goes down. And we also implemented our own accuracy function metric, which is going to evaluate our model's predictions using accuracy as an evaluation metric rather than just loss. So let's now work on training a model. So what should we do first? Well, do you remember the steps in a PyTorch training loop? So to train our model, we're going to need to build a training loop. So if you watch the video on the PyTorch, so if you can Google unofficial PyTorch song, you should find there we go, the unofficial PyTorch optimization loop song. We're not going to watch that. That's going to be a little tidbit for the steps that we're going to code out, but that's just a fun little jingle to remember these steps here. So if we go into the book section, this is number 3, train model, exactly where we're up to here. But we have PyTorch training loop steps. Remember, for an epoch in a range, do the forward pass, calculate the loss, optimize a zero grad, loss backward, optimize a step, step, step. We keep singing this all day. You could keep reading those steps all day, but it's better to code them. But let's write this out. So forward pass, 2, calculate the loss, 3, optimize a zero grad, 4, what do? Loss backward, so back propagation. I'll just write that up in here, back propagation. We've linked to some extra resources if you'd like to find out what's going on in back propagation. We're focused on code here, and then gradient descent. So, or optimize a step. So build a training loop with the following steps. However, I've kind of mentioned a few things that need to be taken care of before we talk about the forward pass. So we've talked about logits. We looked up what the hell is a logit. So if we go into this Stack Overflow answer, we saw machine learning. What is a logits? How about we see that? We need to do a few steps. So I'm going to write this down. Let's get a bit of clarity about us, Daniel. We're kind of all over the place at the moment, but that's all right. That's the exciting part of machine learning. So let's go from raw logits to prediction probabilities to prediction labels. That's what we want, because to truly evaluate our model, we want to, so let's write in here, our model outputs are going to be raw logit. So that's the definition of a logit in machine learning and deep learning. You might read some few other definitions, but for us, the raw outputs of our model 0, are going to be referred to as logits. So then model 0, so whatever comes out of here are logits. So we can convert these logits into prediction probabilities by passing them to some kind of activation function, e.g. sigmoid for binary cross entropy and softmax for multi-class classification. I've got binary classification. I have to sound it out every time I spell it. For binary classification. So classification. So we're going to see multi-class classification later on, but we want some prediction probabilities. We're going to see what they look like in a minute. So we want to go from logits to prediction probabilities to prediction labels. then we can convert our model's prediction probabilities to prediction labels by either rounding them or taking the argmax. So round is for binary classification and argmax will be for the outputs of the softmax activation function. But let's see it in action first. So I've called the logits are the raw outputs of our model with no activation function. So view the first 5 outputs of the forward pass on the test data. So of course our model is still instantiated with random values. So we're going to set up a variable here, y_logits, and model 0, we're going to pass it the test data. So xtest, not text, to device, because our model is currently on our CUDA device and we need our test data on the same device or target device. Remember, that's why we're writing device agnostic code. So this would work regardless of whether there's a GPU active or not. Let's have a look at the logits. Oh, okay. Right now, we've got some positive values here, and we can see that they're on the CUDA device, and we can see that they're tracking gradients. Now, ideally, we would have run torch.inference mode here, because we're making predictions, and the rule of thumb is whenever you make predictions with your model, you turn it into a val mode. We just have to remember to turn it back to train when we want to train, and you run torch.inference mode. So we get a very similar setup here, we just don't have the gradients being tracked anymore. Okay, so these are called logits. The logits are the raw outputs of our model without being passed to any activation function. So an activation function is something a little separate from a layer. So if we come up here, we've used layer. So the neural networks that we start to build and the ones that you'll subsequently build are comprised of layers and activation functions. We're going to make the concept of an activation function a little bit more clear later on, but for now, just treat it all as some form of mathematical operation. So if we were to pass data through this model, what is happening? Well, it's going through the linear layer. Now, recall, we've seen this a few times now, torch and then linear. If we pass data through a linear layer, it's applying the linear transformation on the incoming data. So it's performing this mathematical operation behind the scenes. So y, the output, equals the input x multiplied by a weight tensor a, this could really be w, which is transposed so that this is doing a dot product, plus a bias term here. And then if we jump into our model state dict, we've got weight and we've got bias. So that's the formula that's happening in these two layers. It will be different depending on the layer that we choose, but for now we're sticking with linear. And so that the raw output of our data going through our two layers, the logits, is going to be this information here. However, it's not in the same format as our test data. And so if we want to make a comparison to how good our model is performing, we need apples to apples. So we need this in the same format as this, which it's not, of course. So we need to go to a next step. Let's use the sigmoid. So use the sigmoid activation function on our model logits. So why are we using sigmoid? Well, recall in a binary classification architecture, the output activation is the sigmoid function here. So now let's jump back into here and we're going to create some pred probs. And what this stands for on our model logits to turn them into prediction probabilities. Probabilities. So y pred probs equals torch sigmoid y logits. And now let's have a look at y pred probs. What do we get from this? Oh, well, we still get numbers on a page. Goodness gracious me. But the important point now is that they've gone through the sigmoid activation function, which is now we can pass these to a torch.round function. Let's have a look at this. Torch.round, and what do we get? Pred probs. Oh, the same format as what we've got here. Now you might be asking, like, why don't we just put torch.round here? Well, that's a little, this step is required we can't just do it on the raw logits. We need to use the sigmoid activation function here to turn it into prediction probabilities. And now what is a prediction probability? Well, that's a value usually between 0 and 1 for how likely our model thinks it's a certain class. And in the case of binary cross entropy, these prediction probability values, let me just write this out in text. So for our prediction probability values, we need to perform a range style rounding on them. So this is a decision boundary. So this will make more sense when we go ypred probs. If it's equal to 0.5 or greater than 0.5, we set y equal to 1. So y equal 1. So class 1, whatever that is, a red dot or a blue dot. And then ypred probs. If it is less than 0.5, we set y equal to 0. So this is class 0. You can also adjust this decision boundary. So say if you wanted to increase this value, so anything over 0.7 is 1 and below that is 0. But generally, most commonly, you'll find it split at 0.5. So let's keep going. Let's actually see this in action. So how about we recode this? So find the predicted probabilities in, so we want the predicted labels. That's what we want. So when we're evaluating our model, we want to convert the outputs of our model. The outputs of our model are here, the logits. The raw outputs of our model are logits. And then we can convert those logits to prediction probabilities using the sigmoid function on the logits. And then we want to find the predicted labels. So we go raw logits, output of our model, prediction probabilities after passing them through an activation function, and then prediction labels. This is the steps we want to take with the outputs of our model. So find the predicted labels. Let's go in here. A little bit different to our regression problem previously, but nothing we can't handle. Torch round, we're going to go ypred probs. So I like to name it ypred probs for prediction probabilities and ypreds for prediction labels. Now let's go in full if we wanted to. So ypred labels equals torch.round, torch.sigmoid, so sigmoid activation function for binary cross entropy, and model 0 xtest.toDevice. Truly this should be within inference mode code, but for now we'll just leave it like this to have a single example of what's going on here. Now I just need to count 1, 2, there we want. That's where we want the index. We just want it on 5 examples. So check for equality, and we want print torch equal. We're going to check ypreds.squeeze is equal to ypred labels. So it's just, we're doing the exact same thing, and we need squeeze here to get rid of the extra dimension that comes out. You can try doing this without squeeze. So get rid of extra dimension once again. We want ypreds.squeeze. Fair bit of code there, but this is what's happened here. We create ypreds. So we turn the ypred probs into ypreds. And then we just do the full step over again. So we make predictions with our model. We get the raw logits. So this is logits to pred probs to pred labels. So the raw outputs of our model are logits. We turn the logits into prediction probabilities using torch sigmoid, and we turn the prediction probabilities into prediction labels using torch.round, and we fulfill this criteria here. So everything above 0.5, this is what torch.round does, turns it into a 1. Everything below 0.5 turns it into a 0. The predictions right now are going to be quite terrible because our model is using random numbers, but ypreds found with the steps above is the same as ypred labels, doing them all in one hit, thanks to this check for equality using torch equal, ypreds.squeeze, and we just do the squeeze to get rid of the extra dimensions, And we have out here some labels that look like our actual y-test labels. They're in the same format, but of course, they're not the same values because this model is using random weights to make predictions. So, we've done a fair few steps here, but I believe we are now in the right space to start building a training and test loop. So let's write that down here, 3.2, building a training and testing loop. You might want to have a go at this yourself. So we've got all the steps that we need to do the forward pass, but the reason we've done this step here, the logits, then the pred probs and the pred labels, is because the inputs to our loss function up here, this requires, so BCE with logits loss requires what? Well, we're going to see that in the next video, but I'd encourage you to give it a go at implementing these steps here. Remember the jingle for an epoch in a range, do the forward pass, calculate the loss, which is BCE with logits loss, optimize a zero grad, which is this one here, loss backward, optimize a step, step, step. Let's do that together in the next video.